doke. Well then, because it's going on YouTube. Hi, my name is Prithvi Akella. I am a fifth-year graduate student in the Amber Lab, working on risk-aware safety critical system verification and policy synthesis. I hope you enjoy the cartoon on the left-hand side. In general, it's not. Where there we go. Oh, this is going to be very loud. I apologize. Hopefully these videos play. I'm going to mute. There we go. I'm going to mute myself really quickly so that way it doesn't hopefully come through on your end. But I don't know why these videos aren't playing. These videos are not playing. Wonderful. Let's try this again. Dun, dun, dun. Wow, who knew YouTube was going to just freeze on me the minute I needed it, actually. Okay, I'll just keep talking and maybe, hopefully the videos will play. If not, you'll get the general premise. So general idea is that, okay, the project that I'm funded by is called Test and Evaluation for Validation and Verification. And that's kind of the crux of the work that I'll talk about over the course of today. And so I figured I should at least motivate why it is we study testing and verification. The answer is pretty simple. It's that in the future, robots are going to have to act reliably and safely in unstructured and uncertain environments. And if these videos were playing, you would see on the top left the promotional video for the Star Delivery Service. So they'd be, robots that have to deliver us food across campuses all across America, or people in the Zoox promotional video you see in the bottom left, even building us habitats on Mars for our astronauts to inhabit at later points in time, or in the case of the video on the bottom right, having our robots, in this case, the Robonaut 2, assist astronauts aboard the International Space Station. There we go. Wonderful. We will use a two-phase. So I don't know if you can hear the sound on your end. Just give me a thumbs up if you can or cannot and would like me to change it. Okay, great, wonderful. So, right, in general, though, what we're trying to get at is that the robots that we're asking of robots in the modern day and age to assist us in our daily lives, in the lives in which we live, and those tend to be unstructured and uncertain environments. And as they're assisting us, we'd like for them to reliably and safely assist us. But the reason we study testing and verification is that our robots just aren't that capable yet. And you can see this in the video on the left-hand side. I mean, consider all these failure videos you see from one of the DARPA challenges. Imagine, for the sake of argument, right, that these were exoskeletons, say, housing our grandparents, and they fell down and they otherwise couldn't get up because the exoskeleton wouldn't let them. Or we were in an autonomous car, as seen in this, snippet that you see on the top right, and it crashed, right, because the car wasn't validated. Or, Amazon starts to use these drones to autonomously deliver our packages. They start crashing into our power lines, leaving us without power. In general, right, our systems are not as capable as we would like them to be for them to function as reliably and safely in these unstructured and uncertain environments. And so it's for that reason that we study testing and verification. It's in an effort to increase confidence in safety critical systems and to provide a constructive feedback for controller synthesis that we aim to develop algorithmic testing and verification pipelines for arbitrary safety critical systems. So today, over the course of this short talk, I hope to give you at least a brief overview of some of the work we've done in this vein in our lab, at least the work that I've done on this project, as it concerns these four kind of capstone ideas, which are maximally difficult test generation, uncertainty quantification, risk-aware verification, policy synthesis, and probabilistic guarantees for optimal control. And so I also will pause and ask if people have any questions every so often. So if people have any questions, feel free to voice them now in terms of the general motivation. If not, I'll just continue.
Sounds good. No, this looks like an awesome roadmap.
Awesome. Then with that, I'll jump straight into maximally difficult test generation. And so just to clarify again, what I'm trying to get at today in the course of this talk is a more high-level analysis of the work that's been done with enough math to facilitate a conversation should people be interested. And so what I want to stress then are key concepts, general ideas, and key questions. And so then in that vein, the key question that we had for maximally difficult test generation is how do we generate, oh, sorry, someone saying something? Hello? I think you guys are frozen. Can you guys hear me?
Hey, sorry, I had a little Wi-Fi glitch. We connected to the lab instead of the wireless.
Okay.
I'm back.
Okay, great. Where did I get lost?
You could probably just start by discussing what you mean by maximally difficult test generation.
Great, cool. So then the central question for maximally difficult test generation is the one that you see on the top banner. It's how do we generate difficult time varying tests system behavior? What do I mean by that? Our goal here is to construct a controller agnostic test generation method that is behavior specific. Why do we care about this? Let's say for the sake of argument, consider the hardest test you took in one of your collegiate classes. Now, unless your professor absolutely hated you, that test hopefully wasn't, specifically difficult just for you, the individual, right? I imagine the test was just difficult overall. And so for the fact that the test was difficult overall, you could use it to determine how much or how little a student knew on a given topic. You could also use it to determine the difference in understanding two students had on a given topic. In a similar vein, if you had a test that was difficult for a specific type of behavior on the system of interest, you could use it to determine how well a controller did at effectuating the behavior we care about, or how different two controllers performed in effectuating that behavior we care about. Say controller A was better than controller B because it did better at our test. So this is the reason that we care about generating controller agnostic test generation methods that are behavior specific. As a result, however, we need some way of quantifying system behavior that's a function of the environment that we can manipulate, that's also not a factor of the controller that's on board that system. And so for that purpose, we use barrier function. And so while the definition is on your screen, and I'm certain most people will be familiar, at least in your lab, and if people would like to read this and pause the video if they're looking at this on YouTube, they're more than welcome to. But I'd like to state the key ideas again as to why we utilize barrier function. And there's two reasons why we did that. The first is that barrier functions ascribe to regions in the state space a positive value if the system occupying a state in that region means it's doing something we care about. What do I mean by that? Take this gold region that you see over here, which is the goal region for, say, a single integrator system, as you see in this example set. We can write a barrier function for that single integrator system such that the region where the barrier function is positive is only this goal. That's this function HF. Right? The system occupying a state in that region means it's occupying the goal, means this barrier function is positive. Again, barrier function positive means the system is doing something we care about. Similar premise, right? We have these circles that you see in black, where these be obstacles for the sake of argument. We can define another barrier function, H sub G, where it's positive everywhere the system is not inside the obstacle. Again, barrier function being positive, system is doing something we care about, it's not crashing the obstacle. The second main reason we use barrier functions is for this prescriptive inequality, H dot being greater than or equal to minus alpha H. In general, it provides a class of inputs that render the barrier function continuously positive. That's leaving us inequality with a greater than or equal to, or strictly positive in some finite time, and that's using a strict inequality over here with H dot strictly greater than minus alpha H, with some other assumptions on the right-hand side. So 2 key points that I want to stress: barrier functions being positive means the system is doing something we care about, and there's a prescriptive inequality for the types of inputs that the system must utilize in order to effectuate positivity of this barrier function if it starts negative, or maintain positivity of this function should it start positive. And so maximally difficult test generation then is very simple from an intuitive standpoint, minimize this the system's ability to satisfy this prescriptive inequality. Phrased mathematically then, it's just this min-max problem that you see on the bottom. Okay. And so again, key level, high level key concepts kind of, try and talk about it at that level. What we did is we actually phrased test generation in this format. That's this theorem that you see on the top of your screen. In general, theorems will be there. If you want to pause to read them, you're more than welcome to. Or if you want me to stop and explain them in further detail, also happy to do that as well. But I'm basically just putting them up there in terms of just to act as like this context here. We phrase maximally difficult test generation as a min-max problem, and it has 2 results that are really important. 1, this min-max problem always has a solution. 2, you can prove that the solution is, in fact, the most difficult test of system behavior at that state. And for that reason, that's how we generate maximally difficult tests, and did so for 2 separate tests, a robotarium and a quadruped in our lab. You can see go ahead. Sorry, go on. No, yeah, you can see the types of tests being performed in each of these videos, and I'll explain them in a second. In the case of the simulated video, which goes a little bit slower, and I can show you a little bit better, the ego agent is shown in blue. That's the one being tested. It has to get to at least one of these goals in green while avoiding all of these static obstacles in black, and avoiding this other tester agent, which is moving to its predefined location as defined by this min-max problem in an effort to frustrate this other ego agent's ability to get to its goal. You can see a high-speed rendering of that same object in the video in the middle, and you can see the same happening on the quadruped on this video on the top right. Sorry, on the bottom right. In each of these cases, the tester is doing something that would otherwise correspond to being maximally difficult. In each of these cases, it's moving to cut the agent off from any given path to a goal, for the sake of argument, in the robotarium. And in the case of the quadruped, it basically just parks itself between the quadruped and its respective goal. In general, though, these are sanity checks that whatever behavior or whatever test generation that we're utilizing, again, is not controller specific and is producing tests that we otherwise anticipate to be the most difficult test behavior, prevent any feasible path to the goal, or just park yourself between the goal and the agent. At this point, though, that's the last thing that I have to say on maximally difficult test generation. Any questions?
Yeah, so this argument kind of, okay, so the point that I'm having trouble, the part of the problem that I'm having trouble with is it's only maximally difficult if the controller is trying to do some sort of barrier-based control input, right? Like, let's say your controller was doing some interesting path planning problem where it could plan around these maximal test generation as well, because we know that these barrier functions, unless they're like convex or they have nice properties, you know, they're not doing the optimal thing. So how does this argument get affected here?
You're absolutely correct. I mean, and that's one fault of the method, which actually you hinted at is one of the issues on the next slide.
Okay.
But yeah, you're absolutely correct. And so what you're basically hinting at is that we need some notion of tests just not being difficult at a given system state or for a given type of behavior, but for any type of expressive behavior, we need some way of generating verifiable statements, which is not just going to happen via difficult test generated via barrier. So
okay, yeah, that's fair. Also, for the experiments that you ran, did you have like convexity or linearity properties that you were able to use? Because I'm not familiar with the min-max theorems from KPON, but the duality, I guess that holds regardless. But how did you generate these? How did you solve these min-max problems practically?
Practically, so the idea is that so Kai-Fan's min-max lemma states that as long as you're optimizing over convex or compact sets, and then the cost function is compact concave, right? That always has a solution. As for how we did that specifically, general interior point methods. I mean, we randomly sampled a variety of places and then exhaustively, more or less, tried to search over the input space or search over feasible spaces, and then do gradient descent from there. But we treated the solution, the reported solution, as the optimal solution. In general, how we did this in real time, we gridified the space for continuous spaces, as you see in the Robotarium, and actually in both of these cases, and then interpolated between them.
Okay, very cool. And when you say you represented the set of possible environments, as an example, what does that mean for this Robotarium example?
In the Robotarium, the set of possible environments is the setup of all static obstacles, the setup of goals in that grid, and the starting locations of each of the agents. Also, the setup of static obstacles must allow for at least one feasible path to a goal in order for it to be a valid environment. Otherwise, then
so that's actually a really huge space, right? Like if you've got n squares there, that's like 2 to the n possible environments. Okay, cool.
Yeah. And you will get to this notion of that's a very large space. How is this, single difficult test going to provide me any actual meaning on the, performance of my system overall over, what you just mentioned is actually a relatively large space. And that's issue number one. Issue number two, sorry, also, Caleb, correct? Do you have any other, or sorry, I shouldn't probably say names.
No, you can't.
But if you have any other questions, I know that Dev had questions. So.
I'm good for now. Yeah.
Okay, sweet. Then, as you guys mentioned, right, there are a lot of issues with this first project that we worked on, right? I'm focusing on the utility of barrier functions, which only encapsulate a specific, albeit expressive, set of behaviors, right? That's one, or zero, I should. Number one is that just passing a difficult test has no meaning, right? Even if I can formally prove that a test is difficult, and say for the sake of argument, just because I passed all the tests in my optimization class, doesn't mean that I'm now some expert on optimization. We need some way of making verifiable statements. Two is that robots don't always take the same paths every time. You see this in the case of the Robotarium, the image that you see on the bottom, right? Always asking the robots to move from these red X's to these from these blue diamonds to these red X's. The robots take different paths every time. This is hardware data of the Robotarium. And three, the procedure is practically infeasible to compute in real time. I mean, we're trying to generate difficult tests via solving a min-max problem. That is definitely not going to happen in real time. We need some way of efficiently calculating either difficult tests or verification statements, what have you. And hopefully, given my emphasis on these words, you can see how these kind of issues resulted in the next veins of research I'll talk about, at least as regards uncertainty quantification and risk-aware verification. Just to clarify, you guys can hear me well, even if I trail off sometimes, because I know that I have a habit of doing that.
That's perfect. Yeah, no, that makes a lot of sense. But I just want to say the previous work was a nice way to frame the problem initially. And then I see that you now have a plan going forward. It's cool.
Thank you. Appreciate it. And so unless there are any questions, again, I'm just going to move into some sample efficient results we have for risk measure estimation. And again, the reason that we care about this, robots don't take the same paths every time. If we want to reason about behaviors, that means we're necessarily going to have to reason about random variables whose distributions are unknown. And that's the reason we talk about uncertainty quantification in this regard. Cool. Okay. So then I figure, because risk measure estimation might not be as familiar with the people in this audience, I'll give a little bit of a brief definition of it. And so let sigma be a probability space with sample space omega, event space mathcal f or script f, and probability measure p. Then script L is a set of all random variables, x, defined over this space. And a risk measure, rho, is just a mapping from the set of all random variables to the real line, including minus infinity. So that's a lot of math. Here's a picture. In general, expectation is given via the same notation that you see here. You guys can see my math, correct? Great. Expectation is given via the same notation that you see here. The three risk measures of interest, again, predominantly at large the robotics and controls community, are value at risk level epsilon of x, which is denoted as the epsilon quartile of this distribution of interest. Again, x is the random variable, u is its PDF, and that's shown via this curve. So epsilon, if epsilon is say 0.1, that would be the 90th percentile quartile, when 90% of the probability mass of the random variable lies to the left. Conditional value at risk level epsilon is just the expected value of everything lying to the right of the value at risk. And entropic value at risk level epsilon is just the minimization of the turn-off bound for this random variable. Now, if you don't know what these risk measures are, that's perfectly fine. You can just treat them as, mathematical objects for the time being, because the central question is simply just, how do we estimate these risk measures, as highlighted in red, when we don't know what the underlying distribution is? I took away that curve figure that you saw on the image on the prior slide. Cool. Okay. So I'm just going to jump straight into some results then. It turns out it's actually really easy to estimate these risk measures, even if you don't know what the distribution is. The idea in the case for value at risk is very simply just take n independently distributed samples of your random variable. The maximum such sample is guaranteed to be an upper bound. The maximum such sample is given via zeta star in the theorem. The maximum such sample is guaranteed to be an upper bound to some minimum confidence that's only a function of the epsilon quartile and the number of samples n that you have. Here's examples of us doing exactly that. These distributions, as shown in gray, were not known to us a priori. We took 50 samples of the underlying random variable and reported the maximum such sample via this red line that you see in both of these images. The blue line corresponds to the actual value at risk at epsilon level 0.1. As you can see in both of these cases, the red line is in fact an upper bound on the blue line, and it's with confidence, I think in this case, greater than 99%, that this reported value should in fact be an upper bound on the value at risk level epsilon. So again, stress key points, relatively simple to do. Take a bunch of samples, right? Confidence in the maximum sample being the value at risk is known, and that's this relationship that you see in the theorem that you see on the top right. Okay, I'm going to take a step back. Oh, go ahead. Yeah.
You said that you took like 50 samples. How did you come up with this number? I'm just curious.
Yeah, so the idea is that in general, you would know what epsilon is a priori. So you'd say, I want to upper bound value at risk, in this case, epsilon equals 0.1, right? And I want to provide an upper bound with a prescriptive confidence. In this case, something greater than 99%. I'm sorry, I'm blanking on the actual, what that confidence. But based on knowing what this epsilon is and knowing what your desired confidence is, you can solve for n. Take that many samples and then report the maximum. Cool?
Yeah.
And so just to, again, reiterate, I'm going to take a step back really quickly and now upper bound instead of the other two risk measures, conditional value at risk and entropic value at risk. I'm going to upper bound the expected value of the variable, again, without knowledge of its distribution. Turns out that's also pretty easy. Because we can upper bound the value at risk, we can binarize the distribution given that upper bound and calculate the expected value of binarized distribution, which is necessarily going to be an upper bound in the expected value of the original distribution, again, to the same confidence. And that's what I want to stress. Does that make sense? You can see us doing exactly that in this image on the left-hand side, where again, the red value was calculated by taking 50 samples. The blue value is the actual expected value of this distribution as shown in gray, which again, we didn't know what it was. But why do I care about this? Turns out, via some work done by people from prior, that both the conditional value at risk and entropic value at risk can be expressed as optimization problems over expected values of random variables whose distributions are unknown. So as long as we can upper bound expected values of random variables whose distributions are unknown, we can upper bound the objective functions for each of these optimization problems. And as a result, upper bound both of these other risk measures as well. Same premise as before. Red line is calculated with 50 samples. Confidence is the same. It is in fact an upper bound on the conditional value of risk. Red line is taken via 50 samples. Again, confidence is the same. As a result, it is an upper bound on the entropic value at risk as well. So the key takeaway that I want to leave you with from this section is that even if you don't know what the underlying probability density function is for these random variables of interest, upper bounding or lower bounding the risk measures we care about for these random variables is a relatively simple function of the number of samples we take, and it's also a very sample efficient method. And the reason we care about sample efficiency here, again, is that at some point down the line, we're going to utilize these results to make verification statements. And so each sample of this random variable would be, say, a trajectory of our system of interest. And you can imagine that, if you have to run, say, an autonomous car, you don't want to run 1,000,000 times. You might want to run it, say, 50 times and get a very nice result. That would be much better. Any questions on how what we've done with respect to uncertainty quantification for risk measure estimations?
It's really interesting that it's completely independent of the underlying distribution, which, I mean, sort of gives me the idea that regardless of how big your scale is, how complicated your system is, 50 samples is good for epsilon 0.99 kind of thing.
Epsilon 0.1 with confidence 0.99 roughly, something like that. Yeah.
Sure. Okay. Cool. Okay.
Okay, then great. Then I'll jump straight into how we used these results to inform sample efficient results for optimal decision selection. Okay, great. So general again, what's the key idea in this vein that we care about? We want to efficiently identify good solutions to optimization problems. Why do we care about that? Well, typically, again, down the line, both verification and policy synthesis, in the case of, say, optimal controllers, will all be expressed as optimization problems. And they're also going to be optimization problems that are likely non-convex. Solving non-convex optimization problems, as we all know, is a very hard procedure, but we still need to be able to solve them, at least efficiently, in order for us to determine verification statements or controllers, something along those lines. So the question then is, how do we efficiently identify good solutions to optimization problems? And I should be specific. The types of optimization problems we're going to consider is the following: maximize some reward, subject to X being in some decision space. I'm going to assume that this decision space is bounded, that if it's a subset of Euclidean space, it has bounded volume, or if it's a finite space, it has a finitely many elements. And I'm also going to assume that this reward, here we go, this reward is also bounded over that decision space. This is the only thing I'll consider. Now, for the fact that I've said it like this, some people in the audience who may be more familiar with learning might immediately state, hey, why don't you use, say, Bayesian optimization or Thompson sampling or another one of these techniques? In short, the reason we don't use them, in the case of, say, Bayesian optimization in particular, they make assumptions on the reward function. In the case of, say, Gaussian process regression for Bayesian optimization, the reward has bounded norm in the reproducing kernel Hilbert space of the kernel chosen, and you know what that bounded norm is a priori, but there's no way of verifying that statement. And so if I were to make, say, a verification statement predicated on this function having a bounded norm, which I can't verify, and the corresponding verification statement. So at the very least, I know I can verify these two aspects of my optimization problem relatively trivially, at least again, as it regards verification and policy synthesis. So for the moment, I would only like to make this assumption and move from here and see if we can identify good solutions. What do I mean by a good solution? A decision X star and D is in the 101 minus epsilon percentile, oops, got a percentile there, and maximizing some reward R. If it is better than, say, for the sake of argument, if the epsilon was, say, 0.1, it is better than 90% of decisions X and D. Does that make sense?
Yeah, this is something like a duality argument, but except over non-convex
Exactly.
spaces. Yeah.
And so the key takeaway is that all optimization problems of this type always have level sets over their bounded decision space. And there always exists a random variable X that maps from the decision space back to itself, such that sampling a decision, say the 90th percentile, occurs with at minimum probability 0.1. So if you want to find a decision in that percentile, sample the random variable, take enough samples, you should have some confidence of identifying the decision in the corresponding percentile.
Sorry, I lost you there. Doesn't that depend on the underlying function?
Nope.
Why not?
As long as it's bounded, this is true.
Okay.
Yeah. And the reason for that is simply because as long as it's bounded, you can take, say, and you'll see this in the statement of the theorem here as well, you take the uniform distribution over that underlying set. The uniform distribution maps level sets to percentiles. And so long as the function is bounded, it has those bounded poles. That's it.
Okay, interesting. Yeah.
Yeah. And so in general, then that's expressed formally, that's this notion here, right? Query the uniform distribution over that space, pick the best sample. And again, you're going to see the same confidence pop up, right? The same confidence that we had for risk measure estimation, because we're utilizing those same. And you can see that this actually does work. That's this image that you see on the bottom. So general optimization problem for the traveling salesman is shown here. Minimize over the set of pads, some cost. This cost function is clearly bounded over the set of pads. The set of pads is also bounded as well, under the assumption that the number of nodes for this problem is cool. So in the case of, say, 9 nodes, as you see on the image on the left-hand side, the set of all possible pads is, say, 360,000 plus. But according to this result here, if I want, say, a path that's in the 95th percentile with 95% confidence, I only have to evaluate something like 100 paths. Doing so in the case of the image on the right-hand side, again, 100 uniformly sampled paths. Doing so in the case of the image that you see on the left-hand side, in this particular case, identified the best possible path. Now, if you wanted a higher percentile path with a higher confidence, that's just changing the sample complexity result based on this confidence that you see in this 1 minus 1 minus epsilon. Cool.
Question. So with the traveling salesman problem, doesn't this depend on the size of your space? Like the minimization is over P in paths. Paths depends on the number of nodes. So the n equals 9, that n is different from the n in theorem 3, right?
Yes, sorry. I apologize. I should have changed notation there. So the n over here for each of these traveling salesman ideologies is just the number of nodes. The n in this is the number of.
Cool. But then what tell me if I got this wrong. Whether I have a traveling salesman problem with 9 nodes or 9 million nodes, I only need to sample paths. To get the epsilon percentile, I only need to sample the same number of paths.
That is correct.
Interesting.
The reason for that, just to clarify, I know that's a very unintuitive statement.
Yeah.
That is because percentile statements inherently normalize against the size of your space, right? Being in the 90th percentile means you are better than 90% of your space, or at least as good as 90% of your space. Now, if your space size has larger absolute volume, then yes, the number of things in the 90th percentile increases, but also the number of things you are at least as good as if you're in the 90th percentile increases, but so do the same decisions that are better than you also increase. Does that make sense? Yeah. So in the case of, say, like 9 million pads or 9 million nodes, sure, being in the 90th percentile is relatively easy to find, but it is also possible that being in the 90th percentile gives you no actual benefit, right? It is so far away from optimal that it is not of any use to you whatsoever. Does that make sense? Yeah.
Okay.
So the idea here is, again, what we're trying to identify is good solutions to problems. And the reason I'm rephrasing these good solutions as I am at least as good as a large fraction of my decisions. And it turns out that in phrasing the problem that way, yes, the sample complexity result is known and dimensionally. As a result, and also again for verification and policy synthesis, it turns out solving this problem from a percentile-based method is actually pretty useful and has very intuitive meaning, right? I've developed a controller that's better than, say, 99% of controllers that I could have possibly developed for my system. Or I've developed a test, right? That's better than 99% of tests I could have developed for my system, subject to some behavior, which in general does not need to be expressed now via a convex cost or a convex reward, right? It can be expressed via any type of reward so long as the reward is bounded. And this allows that expressive nature of behavior that you mentioned in the prior, as a question on the prior topic, as to barrier functions are expressive, but they're not super expressive. Could we express different types of behaviors? Yes. Now you can have them expressed via any non-convex objective.
Interesting.
Cool. Any other questions? This is the last slide we have on suboptimal solutions.
No, that's really interesting.
Awesome. I'm glad that you find it interesting. Well, then with that, I'll get to the actual crux of my talk, which is how do we apply these results for risk-aware verification and policy synthesis. Cool?
Cool.
So then with that, right, general question for risk-aware verification is how do you verify worst-case system behavior without exhaustive testing? Again, to give an example, right, I want to say verify an autonomous car. I don't want to have to, drive the car in San Francisco, drive the car in Los Angeles, drive the car in Chicago, et cetera, so on and so forth. Every city on the planet, right? Ideally, I'd like to find some expressive set of behaviors, some expressive set of tests, evaluate the car under those expressive set of tests, And then for the fact that it, say, passes all of these tests, I'm cool with saying that, 99% probability the car is going to function as it's supposed to. That's the kind of general idea behind risk-aware.
Except you need to sample uniformly across all environments.
Yes, exactly. So let's get example aside. There's some nuances that might have to be worked out, but that's in general how the problem is phrased. And you can see in the citations that you see on the bottom of your slide that this is a very well-studied problem for one, and the problem is typically phrased in the following manner, which I'll describe. So in general, the way the problem is approached, take your system of interest, say the Robotarium, that's on the bottom. Extract system trajectories from your system of interest when it is attempting to function in the environments that you care about, and then evaluate them under what we call a robustness measure. This is just some function that outputs a positive value. The system exhibits the behavior you care about, and a negative value if it did not exhibit the behavior. And the more positive the value, the more robustly the system exhibited that behavior, hence the reason it's called a robustness. As a result, then the outcome of this robustness measure is some real valued output, R. And then the nominal verification problem then, again, is expressed in the literature more generally, is minimize this robustness measure R, or minimize the value of this robustness measure R, subject to the set of environments possible for your system, right? And then if the answer,
minimize?
Because if the answer is, well, no, the idea for verification is minimize this robustness of this environments. Because the solution to that problem were positive, that means the system has been verified over all environments. It will always exhibit a positive robustness, therefore it will always exhibit the behavior you desire. If the answer is negative, that means there exists a counterexample, and hopefully you found the counterexample via your option. And again, right, that's how the problem has typically been formulated. The key idea that we had here, though, and what we utilize to solve this problem in a different fashion, is that if you randomize the initial conditions and environments that produce the system trajectories of interest, then the corresponding robustness outcomes of these sample trajectories are just samples of a random variable. And what we're trying to identify then, in this case, is a probabilistic lower bound on that random variable, again, whose distribution is unknown. So we can just use the risk measure identification results from prior to make progress on the problem. And that's exactly what we did. So now it's very similar to the results that I mentioned from risk measure estimation in the prior slide. You'll see the same confidence popping up. It's just that the actual random variable now has some intuitive meaning. It's this evaluation, the robustness evaluation of a system trajectory, and you're getting a probabilistic lower bound on the robustness evaluation of system trajectories. But now it doesn't matter what the distribution is. So it doesn't have to be uniform, it can be whatever distribution you care about. Cool?
Cool.
And so long as you take independent samples from that distribution, you get some minimum robustness evaluated over system trajectories, and that's what's utilized in this probabilistic argument you see here. The probability that the system will always exhibit robustnesses greater than your minimum value is greater than or equal to 1 minus epsilon. And your confidence, again, is that same function that you saw from prior, 1 minus 1 minus epsilon. This actually works. So you can take the Robotarium as a case study in this case, say that the traditional specification for the Robotarium is to always move from any initial condition in your space, regardless of the number of agents, and always get to their goals without crashing. You can see on the right-hand side, a randomization of initial conditions is shown in blue, and a randomization of goals is shown in gold. In this case, I did uniformly sample over initial conditions and goals. In the image that you see on the left-hand side, running at 8 times speed, we identified a counterexample. And this occurs with relative frequency. And you also know why this counterexample occurs as well, because you recorded the corresponding system trajectory. In this case, the counterexample occurred because the Robotarium robots use a continuous time barrier filter. And in this specific case, the continuous time barrier filter, zero order held over a 30 hertz interval, or what time interval of 30 hertz, leads to a violation of safety because of at that moment in time the system was safe if it took that input, but zero order held for a little bit of time, the system wasn't safe as the system progressed. Excuse me. And so that's why you can use this method to identify counterexamples, but you can also use it to make verification statements. And this also hints at a relatively useful aspect of this procedure as well. So for both a 3 robot system and a 6 robot system, we repeated the same verification procedure, randomized with initial conditions and randomized goals. This is data for the system simulator. And we repeated this procedure 50 times for each system. In each case, we identified a lower bound, so this R star n, which was positive. And we took, say, 2,000 more trajectories of our system in order to verify that this probabilistic statement on the interior held. As you can see in all 100 cases run, the statement held. But notice that I don't have this probabilistic lower bound is not a function of the number of robots in my system. It's not a function of the dimension of my problem. Again, because percentile arguments, as I mentioned way back when, inherently normalize against the size of your space. And so long as what I'm doing is taking all of my system trajectories of interest and just mapping them to the real line via a robustness measure, the thing that I care about is always some real valued output. It always exists on the real line. So the sample complexity for bounding such an output is always known to us, independent of the dimension of the underlying problem. Does that make sense? And that's the general result for a score verification. Last slide I have on this topic. So again, you don't have to exhaustively test your system. You express the outcomes of your system as a random variable when evaluated under this robustness measure. Take random samples of this robustness measure via randomization of initial conditions and environments. Evaluate the corresponding robustness measures. Minimum one is guaranteed to be a minimum value to some minimum probability, and a confidence that is known to you. Cool?
Very cool.
Yeah.
Awesome. Any questions before I move on? Okay. Then we can start talking about policy synthesis, right? And so in general here, the now motivating question is, okay, how can we use our probabilistic verification algorithms to facilitate rapid controller synthesis? Because as I mentioned in the first slide that I had, right, the reason we're doing all these things is to generate pipelines to increase confidence in our safety critical controllers for our systems of interest. And so at the end of the day, we need some way of wrapping around this pipeline, a controller synthesis type. And so you see this cartoon of probabilistic verification happening on the top left. I'm going to make one more additional assumption, that the controller for this system is parameterized by some fashion. For the sake of argument, I take the exact control barrier filter that exists in the Robotarian systems, and I say the function that is otherwise used in this inequality is the thing to be parameterized, this function alpha. If they have 10 such functions, alpha 1 through 10, then my parameter space P is just 1 through 10, the indices, and they correspond to. Now, the general optimization problem then is to try to figure out what function I should utilize there. And so the key thing from probabilistic verification is that what we get is a robustness cutoff R star n, such that the system exhibits trajectories that are at least R star n to some minimum probability. And so the key insight then is I can just take the output of probabilistic verification as the reward for an optimization problem over a bounded decision space, where so long as the robustness measure is bounded, this reward is also bounded as well. And I can use then the sample efficient optimality results from prior to identify, now in this case, percentile controllers that are in the 99th percentile with respect to maximizing this minimum probabilistic baseline for the sake of it. And that's exactly what we did. So to highlight again, the very key point is that we're taking from our prior probabilistic verification results, again, just treating theorems as pictures, this value R star n, which is the probabilistic lower bound, and we're saying that the outcome of our parameterized controller, the reward of our parameterized controller, is this probabilistic lower bound. Phrased formally, it's in this theorem that you see. Pictographically, this is the data, and I'll explain this data. So what you see in the image on the left-hand side is the outcome for the controller that arose as a result of taking this percentile-based approach for policy synthesis. In this case specifically, we wanted a controller in the 99th percentile with respect to maximizing that minimum probabilistic reward for a robustness measure, which identifies a positive value for the system that you see ambulating on the left-hand side, so long as it makes non-trivial progress towards its goal within a certain time frame and doesn't crash into any of these static obstacles as shown in gray, and any of these moving obstacles as shown via these red dashed circles. Now, another aspect of the environment is these moving circles will always stop when they get to within 0.2 meters of my agent of interest. So that way, if any crash occurs, I can always identify that the agent was the one that caused the crash and not the randomly moving obstacle, which does move faster than my agent. And so this is an aspect of the environment that I can encode when randomizing over such an environment. And now as a result, then I randomize over these environments. I evaluate my randomly sampled controller over each of these environments, and I pick the best one that performed the best in each environment. That's this red line that you see over here. It is in fact in the 99th percentile, because if you evaluate, as we did over here, 2,000 more controllers and evaluate their corresponding rewards, the distribution shown via predominantly the singleton that you see over here, but it does have a very large tail. The 99th percentile for that distribution is shown via this blue line. And for the factor line on the left, I am actually in the 99th. Expressed as a minimization problem, just to use some wonky mathematics. Cool.
Cool. Okay.
And you can see that this controller actually does what it's supposed to do in this image in the video on the left-hand side. It does always make non-trivial progress towards its goal. and it doesn't actually ever crash in any of these randomly moving obstacles. So again, key points, we take probabilistic verification, the output of which is some real value. We make that the objective function for an optimization problem. Now, so long as the robustness measure for probabilistic verification is bounded, and the decision space for my policy synthesis problem is also bounded, this is just a bounded optimization problem. I can solve for it via the same sample efficient results from prior, and it has very good intuitive meaning. I've identified a controller that's better than, say, 99% of controllers I could have possibly developed for my system, so on and so forth. Any questions before I move on? This is the last slide I have on this topic.
No, I think that's fair. I'm just trying to see one thing. So when you're trying to run this optimization over policies, does that mean you run verification for each of the policies?
Yeah.
And then choose the best one, essentially?
Yep, exactly.
Okay, I see.
Yeah.
And then would you do another round of verification afterwards to verify the final policy that you found, or no, you don't really need to, right? Like,
you don't really need to, right? Because that was already done as part of the policy generation scheme.
Yeah. Okay.
Yeah, and just to clarify again, right, the benefit of this, again, the rewards do not need to be, in general, they're not going to be convex. The decision space for your problem doesn't also have to be convex as well. You can really think of whatever decision space you want. It just has to be bounded. And because again, right, as long as it's a bounded objective over a bounded decision space, it has level sets, and the uniform distribution will necessarily map to 100%.
Okay.
Cool. So then now I'm just going to talk about some stuff that I'm doing at the moment. These are like the last few slides that I have, and I'll go through them relatively quickly because again, I'm just trying to give key ideas and high-level concepts. So in general, now the question is, can we verify the models we use for controller synthesis, right? And the idea there is very simple. We have models for our systems, we use them for controller synthesis, but we know that these models are inaccurate. And so what I mean there is that if I have a model, I can say at some discrete time step that my model evolves to some simulated model state, but my true system, starting from that same initial condition, might evolve to a different state. But I can record those two, successor states, as I'll call them. I can identify the norm discrepancy between those successor states, and that's just the now measure of interest that I care about. Randomize over initial conditions and inputs, you get a random sampling of what that norm discrepancy is, and you can identify then as a result, because now it's a random variable, probabilistic upper bound on what that norm discrepancy is. You can then, for controller synthesis, as you see in this video that you see here, I'll pause just to make it clear. The video on the top left is the augmentation of our nominal model with stochastic disturbances sampled from within that norm discrepancy bound. And then you can see that the stochastic system then outputs effectively an envelope that the true system evolution will otherwise lie in for any given controller. So you can then evaluate or verify whatever controller architecture you want against this stochastic system, as you see on the left-hand side, or a given robustness measure of interest, and develop policies purely on the computer that when you implement them on your real system, actually do the things you care about. Because you know that the stochastic model of interest is a decent approximator of true system behavior, as shown via this gold lines, gold regions encapsulating the blue trajectories taken by my hardware system. And so in the image you see on the bottom right, on the right-hand side, in this case, the boxes were just randomly placed by grad students in the lab and also by uniform sampling as well. And in each case, they were tried to, the goals were also randomly changed. So the quadruped had to identify, again, via controller, a path to the goal. But what I want to stress is that in all 40 cases, the quadruped never crashed and always went to its goal. And this, again, is expected because we verified the controller, again, via these random verification techniques. We had a very high probability of success on this controller that was then effectively implemented on the quadruped. So this is the data of that. You can see that every time we basically just express it as a random variable for identifying the sim to real gap, we report this red line as the maximum sim to real gap. It is in fact an upper bound on the probabilistic sim to real gap. We don't have holistic data for the quadruped because that just takes time, and the other grad student in the lab needs his robot, and I can't use it all the time. We can see that when we implement these policy synthesis procedures or verification procedures on the synthesized policy, the red lines correspond to the minimum probabilistic robustness. It's a lower bound on the true value. Red line corresponds to the minimum probabilistic robustness. It's a lower bound on the value. So key takeaway, we can express the sim to real gap, augment our models to generate stochastic models, and then verify our controllers purely on the computer against those stochastic models, such that when they're implemented on the real system, they work more or less out of the box. Second key idea. Oh, go ahead.
Sorry. So I'm trying to understand where does like input output stability come into this picture? Because, you know, for these kind of dynamical systems, at least for the quadruped, you've got relatively nice properties like input to state stability, but do you have to assume that when you try and apply these techniques?
So yeah, let's take for the sake of argument that, like, say for the sake of argument, your system is chaotic, right? And you had some behavior of interest that you wanted to express, excuse me, for that system. Now, one of two things could happen. For the fact that your system is chaotic, and let's say that your behavior of interest constrains against chaotic behavior. If it happens frequently enough, it should show up in the kind of distributional data for your system. And as a result, then, if you want to optimize for controllers that constrain against such chaotic behavior, you should naturally shift the distribution into one such that it's always positive even for that chaotic behavior. Does that make sense?
So not really. So let's say you had a unicycle type robot, and the unicycle robot is non-holonomic. So now if you let's say want to keep driving it in a straight line, you don't have the control authority to go perpendicular to your heading, right? Mm-hmm. Now, if your robustness measure was, you know, how well are you able to travel perpendicular to you, you would end up with a very poor robustness, right? Like essentially it's unable to do this.
Sure.
How does that then lead to a controller that, you know, is
I see.
Able to move to in the perpendicular direction?
So kind of, if I may generalize your question slightly,
sure.
The notion is of what you're asking is, okay, let's say for the sake of argument, I have some objective function for an optimization problem, and I know it has, say, a maximum value. And that's a maximum value. This is a maximum value that I care about, say, for the sake of argument. And there are some decisions in my decision space, or there are some decisions that I know for this function of interest that exhibit something close to this maximum value. There are controllers that I know for my system of interest. I'll make it turn such that it'll, say, increase the robustness of my system. Are those values aspects of my decision space? So are those decisions, do those decisions actually lie in the decision space that I'm utilizing for this optimization problem, right? Do those controllers actually exist in the space of controllers that I'm sampling over to maximize this robustness? Does that make sense? Is that right? And so the reason I phrase that question that way is you're absolutely correct. You're making an assumption that for this problem of interest, when you're expressing it as an optimization problem, that there exist decisions in your decision space that yield this non-trivial behavior that you care about. If they don't exist in your decision space, you're never going to find them, right? Because they don't exist in your decision space. And so you're kind of hosed from the get-go, if you will. So you kind of have to make the assumption that, yes, you are sampling over a large enough or expressive enough space that you can identify in some given percentile something that maximizes your reward for the sake of argument. And this notion of, say, both domain shaping and reward shaping then is a very integral aspect of how you start setting up these optimization problems, right? If the controllers you're looking for are, say, a needle in a haystack with respect to the decision space you're utilizing, then yeah, it's going to be relatively difficult to identify a decent controller, right? If they aren't a needle in a haystack, they exhibit some non-trivial volume, then it might be significantly easier to identify. So that aspect of the question that you've asked, domain shaping and reward shaping, is not something I've considered, partially because that's a very hard problem in and of itself. And so for the sake of argument, I'm just going to make the assumption that, you know, once you have posed the optimization problem, you're fairly confident that something exists within your decision space to make non-trivial progress on the reward that you have. Does that make sense?
Okay.
But it is something that we would like to move towards in the future. Just very briefly, because we're almost about to run out of time, you can do this online as well. We did this in the case of drones. Videos. There we go. They're playing now. Great. We did this in the case of a drone that we have in Joel Burdick's lab, actually. I work with Skylar. She's a grad student here as well. General premise, right? Same kind of model discrepancy analysis, just done online. So as the system is evolving, calculate discrepancies, see if you can augment the model, and see if you can use this, you see if you can use the new model discrepancy in terms of, say, like an ISS Lyapunov controller to reject against disturbances and basically better flight. And you can kind of see that in both these cases, as you see here. As the system is collecting data, the controller doesn't do very well. But then once the system has collected all the data and then augments the controller with these disturbance bounds, it starts oscillating through these waypoints and faster rates. it starts projecting the disturbance to meter per second wind, in the case of the video on the bottom, very well as well. General premise again, right? You can use these things online. Again, sample efficient results to robustify. Some stuff that I'm moving towards in the future. In general, can we tighten our risk measure bounds, right? Because even though we have sample efficient results, they may be conservative. Because all I'm trying to do is upper or lower bound these risk measures. They could be arbitrarily bad upper or lower bounds. You can constrain against this a little bit, especially in verification and policy synthesis, by just generating bounded objective functions. So this constrains against the arbitrarily bad nature of these upper or lower bounds. The second is, can we use our optimization techniques to identify sets of interest? So this would be corresponding to the question that you asked of like, does a controller that actually, realize a certain minimum robustness exist within my decision space? Is that something I can identify via these procedures? That's something we'd like to move towards. The third is, can we use our optimization techniques to discriminate between different objectives? So this is the other end of that same question. I don't know what my objective should be to effectuate the behavior that I want, but I have some idea that it might exist within this, say, set of objectives that identify the objective that best encapsulates my behavior from that set of objectives. The fourth is, could we make probabilistic guarantees for model predictive control? This is something that we're actually submitting to IROS, which turns out you can, because optimal controllers are expressed as optimization problems over bounded decision spaces. This is a problem you can take a percentile method to solve. Notions of recursive feasibility and maximum controller runtimes are also expressible as optimization problems over bounded decision spaces. So they're similarly able to be solved via these random variable results. The fifth one is, can we verify arbitrary assumptions? And the sixth is, we provide a framework for probabilistic Nash equilibria. Again, min-max problems are just optimization problems. Maybe we could find probabilistic Nash equilibria for non-convex min-max problems, which I imagine would be a very interesting result just from a mathematical perspective. This is in general the last slide I have in my talk. I know I went a little bit overboard. I apologize, but I hope you guys enjoyed it. Any questions?
No, we really enjoyed it. And yeah, I mean, we got to ask questions, and that's great. This is like the main reason I wanted these seminars, because like it's so difficult to ask questions while people are presenting in big seminars. And I just want to be able to like stop you and be like, I don't get it. Let me ask you a question. So yeah, this is awesome.
Good. I hope at least was well, for one, you at least understood something of what it is that I do, maybe not all of it. And if you have any more questions, feel free to ask. I'll make these slides available to you guys if you guys want to use them later on for whatever reason. Cool.
Yeah, I'll probably bring this up with the lab as well. Have them take a look at it, because I know Hartik's been doing some amount of stuff with trying to optimize parameters and like search for parameters in these non-convex spaces, and he's been struggling to like give bounds on it or give guarantees. This would be like an interesting. This might be a way to give these kind of bounds on. Even if you're doing like Bayesian optimization, you can like now bound how correct your solution is or how close to correct your solution is.
To clarify, this method as it currently stands will not bound how close you are to optimality, because it's only comparing against the decision space and not against the reward, or not against optimality. That is something we're moving towards, and I think actually I have some ideas as to how to get there. So the general result would be you use a percentile method. This gets you. Okay, we're good. Yeah, so this right. So you use a percentile method. The percentile method basically states that, okay, you have some solution that's in the 90th percentile, but you could potentially also express the deviance from optimality as an optimization problem, which again, what optimality is, but that would just be an aspect of the distribution that you don't know. And then so you could also say that, okay, this 90th percentile result is also no less than, say, I don't know, a factor of 2 from optimality. And that would be like the kind of general result that I would like to get to. That requires some work, and I'm not entirely certain how to do it, but I think it would be a very useful result for what it's worth. So
you would have like some probability of being within a factor of 2 from optimality.
Yeah, or like the method would spit out whatever that factor is basically.
Sure. Yeah, that's interesting, because you can imagine building like a really nasty case, right? Like you could have like a very, like if you like in a scalar optimization sense, you could have like a really really deep well, and the optimal value is right at the bottom of that well. So like you can sample as much as you want, but you might not ever hit that one point.
A lot of these results exist in a probabilistic sense, and because you're always taking sample-based results, right? There's no probability 1 confidence of any result. but you can get very close to probability 1 based on taking a large number of samples. And so in the case of the well, right, if it's a continuous well, right, you can imagine if I take millions on millions of samples, I'll get arbitrarily close to a sample that's next. Excuse me.
Yeah,
Next.
yeah, that's fair. Very cool. I'd be interested to see how this works for like mixed integer optimization, because you know, there's all these, even in the convex case, these problems are like, they take forever to solve. And they have duality gaps, they have bounds, but I wonder if they compare to the bounds that you can provide. You know, do you get better estimates of the duality gap? Or rather, do you get duality gaps are exact and conservative? Do you get tighter bounds that are still correct on these mixed integer QPs?
I don't think you're ever going to get a result that goes with respect to optimality with just the percentile result. But as it regards utilization of these results for mixed integer problems, I mean, at the end of the day, that's a direct translation of the traveling salesman type ideologies, right? You can imagine that you change the objective for the traveling salesman problem to some convex optimization problem, then that's effectively a mixed integer problem. Right. Under the assumption that, you know, per every integer, the optimization problem is convex, in which case then you just have to solve the convex problem to evaluate your reward or your cost or whatever it is, right? So it would definitely work. You just get, in this case, say, an integer and other decision that is in the 90th percentile of the space of interest or 99th percentile of the space of interest, but that's not going to make a statement as to how close to optimality such a decision would be.
True, but the reason I bring that up is because the space is much more, it's discrete, right? Like if you like Boolean variables on 0 and 1, the space of sampling could be
it's still finite though, right? Even if it's like
still, yeah, never mind. Yeah, you still have the 2 to the n problem. You still need to sample over 2 to the n space. Okay.
But I mean, that's still doable. Like uniform sampling over 2 to the n space, as long as n is bounded, is still doable, right? Imagine a vector, right? You just sample 0 or 1 for every element of that vector n times, and that's a sample from that space. That's uniform. That you know that sample. And so as a result, like in general, I find that like, so yes, you're right. You need to be able to uniformly sample over your space of interest. I venture to state that so long as it's a bounded, as long as it's a finite dimensional vector in Euclidean space, such a procedure is relatively easy to do, relatively in quotation marks. And as a result, you know, you can utilize this procedure. But yes, if you cannot sample uniformly over that space, you're hosed from the percentile standpoint because there is no then relationship between level sets and percentiles.
Right. Very cool.
Thank you.
Very cool. Yeah. Any questions from Caleb or the person on the call as well?
Definitely good. It's really informative. Definitely. Yeah.
There's someone. Oh, yeah, I didn't know that.
There's another person on the call.
Cool. I hope you enjoyed the talk as well. Yeah. All right. Well.
Yeah, I'll put this up on YouTube, and I hope to see you in Detroit.
Me too. See you soon.
When you come around, please come visit the lab.
Yes, for sure. I'll hopefully have a job then, so we'll see what happens.
Fair enough.
Okay, I'll see you soon, man. Have a nice day. Bye-bye.
See you. Thank you so much.
Anytime. See you soon.